In this video, we're going to look at some examples of partial fractions. And what that means is we're looking at a technique of integration which is useful for integrating rational functions. So let's get to it. Here's your first example. So how would we integrate the, oh, sorry, hit my watch here. How would we integrate 1 over this x squared minus 3x plus 2? So this is not going to use substitution, integration by parts, trigonometric. Well, maybe trigonometric substitution would help, but let's ignore that for the moment and see that there's a simple algebraic way of solving such an integral, and it's by the technique of what's known as partial fractions, or as I sometimes call it, reverse common denominatoring, although that's not a word. So here it is. You may or may not have learned in algebra, but you can rewrite 1 over x squared minus 3x plus 2 instead as a over x minus 1 plus b over x minus 2. And the beauty of doing this is that this function and that function, once we find specific values for a and b, well, those are simple u equals x minus 2 and u equals x minus x, or the u equals x minus 1 and u equals x minus 2 substitutions. So it's a piece of cake to integrate once we make that algebra. So here's the algebra. Excuse me. You can see how it works out. Multiply both sides by the denominator. Cancel, x minus 1 with x minus 1 on this term leaves me x minus 2. X minus 2 cancels and leaves me x minus 1 on that term. On the other side, I just get 1. So to solve this equation for a and b, since this is an identity for all x, we can just put in x equals to 2 and x equals to 1. Now, admittedly, you might wonder about that because x equals 1 and x equals 2 are not allowed in the domain of the original function. But nevertheless, it works. You can calculate it in the limit. But anyway, subtleties aside, here we get a equals minus 1, we get b equals 1, and you can see then that this is just a plain old identity. All right. Again, no clue how to integrate that. This guy easily integrated, and that is partial fractions. Is the idea is to take your given integral and take the function you're given and change it to something that is easy to integrate. In fact, that's pretty much the idea of every integration technique we've looked at this semester, isn't it? We always are trying to take something we don't know how to integrate and convert it to something we do know how to integrate, and it's just another chapter in that story. So there we go. Can't integrate this, can integrate that, and natural log of abs of x minus 2 minus natural log of abs of x minus 1. So, all right, so first example of partial fractions decomposition is if we have a quadratic downstairs and that quadratic factors, we can write it as a sum of linear reciprocal functions like that. Now, the numerator being 1 really had nothing to do with this, right? If we had instead had 3x plus 10 over the same denominator, the partial fractions decomposition a over x minus 1 plus b over x minus 2 would have been the same, in the same type, right? I mean, the actual values for a and b would be different. All right, you'd actually have to work that out. By the way, you're not alone in doing this. I don't discourage you. In fact, I would encourage you to consider using, at least only for homework, all right, not for the test, but there are websites where if you ask for like the partial fractions decomposition, for example, wolframalpha.com, if you were to say partial fractions decomposition of this expression, it would actually find the a and b for you. So you can check your work. I would encourage you to find ways to check your work, but you need to make the work your own in the end, of course. All right. Now, let's see here. Your instructor might feel otherwise, and if your instructor feels otherwise, you must listen to your instructor, if I'm not that person. Or even if I've changed my mind at some future point in time. All right. I might disagree with my current me, might disagree with my future me. If my future me is your instructor, then you need to listen to future me. Just saying. Anyway, here we go. 3x plus 2 over x cubed minus 4x squared. So the first order of business is to factor the denominator. All of these partial fractions are based on the proper factorization of the denominator. All right. So we have 3x plus 2 over x squared times x minus 4. And the degree of the denominator will determine how many undetermined coefficients you have in the partial fractions decomposition. A, B, and C are the undetermined at the moment coefficients. And so this x produces an x and an x squared and an x minus 4 as it happens. And then we multiply by the denominator, both sides. That leaves me 3x plus 2 is a times x minus x times x minus 4, the things that are not there. For b, the x squared cancels out in the denominator, and for c, we're just left with x squared because the x minus 4 cancels. And I've decided to label this Pac-Man. So I think about it this way: if Pac-Man eats x equals 0, nom nom nom, then that and that are gone, and it just leaves us the middle term, which is ever so lovely because then 2 is equal to minus 4b, which means b is minus a half. If we feed Pac-Man 4, nom nom, he gives us 14 on the left-hand side, and he gives us 0, 0, 16 next to c. Therefore, c is 7/8. And finally, if we feed Pac-Man the number 1, which is, by the way, I just picked that, all right? Why did I do 1? I've already used up the zeros, which were 4 and 0 for this denominator. So you could pick literally any other number. I just picked the number 1 because it's easy. So 1 times 3 is 3, plus 2 is 5, and then it's equal to what? 1 times 1 minus 3, 1 minus 4 is minus 3. Again, minus 3, and 1 squared is 1, so we get this equation, which gives us 3 times a is equal to c minus 3b minus 5. I rearranged it like that because I already know b and c, trying to find a, and there it is. A is minus 7/8. Consequently, we have taken this given rational function, which was kind of scary, and converted it to a sum of what I call basic rational functions. All right, basic rational functions. I call these basic rational functions. And the nice thing about basic rational functions is that you can integrate them by actually first semester calculus techniques for the most part. So here we go. This integral is equal to that integral by algebra, and we can integrate this, that, and that by basic u substitutions. This gives us, or just its an elementary integral. So minus 7/8 natural log the absolute value of x. This integrates to 1 over 2x, and this integrates to 7/8 the natural log the absolute value of x minus 4. The absolute values are important. Do not forget to put absolute value there. If you put parentheses, your instructor really should take off points. Just saying, it matters. All right. Next example. Here we face the integral of 8x plus x squared plus 2 over x cubed plus 4x squared plus 5x. As I say every time, the first and most important step is to carefully factor the denominator. All right, so we carefully factor the denominator by factoring out x, and that gives me x times x squared plus 4x plus 5. Now this guy right here does not factor over the real numbers. It's what's called an irreducible quadratic, or your book perhaps in algebra called it a prime quadratic. The point is it has complex zeros. In fact, the complex zeros of this quadratic are exactly minus 2 plus or minus I, but whatever. The point is that we've got x times this irreducible quadratic. In this case, the partial fractions decomposition looks a little different than what we've seen so far. I would write it like this: a over x plus b times x plus 2 plus c over x plus 2 squared plus 1. Now, your textbook either doesn't talk about this or would sometimes, some textbooks put a bx here. And that's fine. It just means that their b and c is not my b and c. It's not a big deal. The reason I put x plus 2 here is because I'm lazy. And when I get to the integration, I want it to be as simple as possible. So let's go through it. Multiply by the denominator, and then evaluation at x, at appropriate x will yield good equations. I've found for a problem like this, if I evaluate, of course it's 0 because I've got an x here like that. So plugging in 0, excuse me, makes this term essentially go away, right? Plugging in 0 zeros out that, and it just leaves me a times whatever that works out when I plug in 0, which is 5. So I get a is 2/5, great. And then the other, it's not a 0 technically, but if you plug in minus 2, that's kind of nice because it makes these guys go away. So plugging in x equals minus 2 is pretty nice. On the left-hand side, I get minus 10. On the right-hand side, that zeroes out, that zeroes out. I'm just left with a minus 2c, because x equals minus 2. And since I already know a, I can find c. So c is 26/5 as it happens. And then finally, I need something else, right? Because there's 3. I need to figure out the third one, I think. So I usually pick another value which is giving nice arithmetic. X equals 1 often works. And so I plugged in 1, solved for b, plugged in the numbers, carefully plugged in the numbers, and I get 3/5. Alright, so there you have it. This is equal to that. And the advantage of the right-hand side is that I can integrate that, 2/5 natural log absolute value of x. And this I can break up into 2 pieces, right? What are those 2 pieces? Well, the 2 pieces, mind you, the first piece is from the x plus 2. And the reason I put that x plus 2 there is because then when I get to this step, I'm like, aha! I can make a w equals x plus 2 squared plus 1 substitution. And then the top would be 1/2 dw, which is why I got 3/10 here instead of 3/5, because I put the 1/2 of the dw into there. And this guy, well, that's a trig substitution. We talked about that. Or we're talking about it now at least. This is a tangent substitution. Tangent equals x plus 2. Then the denominator becomes secant squared. The numerator becomes secant squared theta d theta. And we're off to the races. And there you go. So the answer, 2/5 not log of the absolute value of x. 3/10 the natural log of the absolute value of w, which for me was x plus 2 squared plus 1, which remember, uncompleting the square gives us back x squared plus 4x plus 5. And finally, this guy ends up giving us 26/5 inverse tangent of x plus 2 plus a constant. And that's how it goes. Let's look at another example. Example 4. So the example last case was a little bit nicer in the integration than it generally is the case. I'll show you what I mean. So this one, because last one I could do a, last one I was able to actually, I said trig substitution, but actually if you look at the last one, what I did was what? I made a w substitution for both of these. And I made a w substitution for that one, and I actually made a u substitution for the other one as well. So I was actually able to use I was able to use u substitution of sorts for both of these. Usually you got to do trig substitution for one of them. Alright, so here it is. This is a basic rational function. How do we integrate it? We complete the square in the denominator. Alright, so if you complete the square and you get plus here, there's really nothing more to do. Alright, you just got to face the integration. Partial fractions doesn't help you. Partial fractions just gets you here. Now, alright, so what I do is I break it into 2 pieces, x plus 3, and then 13 is 10 plus 3, right? So this is just algebra. I broke that 13 into this 3 and that 10. This piece, I can make a w equals denominator substitution, which gives me dw is 2 times x plus 3 dx, which gives me dw over 2w for this piece. This other piece here, if I make x plus 3 equal to 4 tangent theta, then this denominator becomes 16 secant squared theta. But the dx becomes 4 secant squared theta d theta. The secant squareds be canceling. And that leaves us with like 40 over 16 d theta, otherwise known as 5/2 d theta. Integrate. And we've got 1/2 log of the denominator, the original problem, 5/2 theta plus a constant. And then I want to take the theta and convert it back to x. But remember, tangent theta is x plus 3 over 4. So there you go. The integral is 1/2 this log plus 5/2 this inverse tangent plus a constant. And that's how you do it. Now, again, this one, we didn't really do partial fractions, right? The partial fractions technique was not needed here because what we're starting with is already as simple as you can get. So, I wouldn't say this is partial fractions. I would say this is just integration of a basic rational function. But that's part of the partial fractions technique. We have to learn how to integrate the things that come from partial fractions. All right, so I've shown complete detailed solutions 1 through 5. And now I want to indicate just how to set up the partial fractions without doing the complete algebra or integration. The point here is you could do the algebra and find a, b, c if you wanted to. And then we could integrate the resulting expressions. That said, what I'm doing right now is to just set up partial fractions decomposition, partial fractal decomposition, as we sometimes say. So perhaps on your test, your instructor might give you a problem which says, just set up, but do not integrate the following rational functions, partial fractions, decomposition. In that case, what we want you to do is to just do like this, right? So essentially, your job then in that kind of problem is just to carefully factor the denominator and then write down the partial fractions. Now, there is doubtless in your text a list of what are the complete possibilities for partial fractions, but I'm trying to illustrate by example rather than writing a general theorem here. I hope you can forgive me for that. If you're a math major, you probably should be taking this course residentially anyway, so just saying. All right, here we go. So we got this, which factors like so, right? Difference of x squared squared and 4 squared, which gives me x squared minus 4, x squared plus 4. Now that guy is done. That's irreducible, can't be further factored, unless you bring in complex numbers, right? Complex numbers, x plus 2i times x minus 2i, but that is not allowed here. We're looking for real factorizations. Now this guy, difference of perfect squares again, so x plus 2 times x minus 2, and there you have it. This linear times that irreducible quadratic is the factoring of the denominator. As a rule of thumb, this is fourth order, which means I should have 1, 2, 3, 4 parameters in the partial fractions decomposition, as I do. So I get a over x plus 2 from this one, I get b over x minus 2 from that one, and I get cx plus d over x squared plus 4 from the third one, because again, this is an irreducible quadratic. This and that could not be more different. In terms of real factoring, this has 2 real zeros. This one never crosses the real axis. If you look at the graph, y equals to the quadratic. Very different algebra. All right, next example. 7. We have here x squared minus 1 squared. So I square that. This is x minus 1 times x plus 1 squared, which gives me x minus 1 squared times x plus 1 squared. Make sure you understand this step. The numerator, the key about the numerator here is that it has an order which is smaller than the denominator. If the orders match, or if the numerator's order is larger, we have to do something else I'll get to eventually. Now this x minus 1 squared produces a over x minus 1, and then plus a b over x minus 1 squared. That's what you have to put when you have a factor squared like that. And likewise, this produces a c over x plus 1, d over x plus 2 quantity squared. That's the partial fractions decomposition. Next example. This one here, let's see here, what's going on here? We've got x plus 2x plus 1, x squared plus 3x plus 2. So this and that both factor. This one factors into x plus 1 squared. That one factors into x plus 1 times x plus 2. Now I cannot do the partial fractions until I combine things. You gotta complete the factoring of the denominator before you can logically and carefully do partial fractions. So we got x plus 1 cubed times x plus 2. This x plus 1 cubed produces this, and this in the partial fractions decomposition. This x plus 2 produces the d over x plus 2. Again, my numerator, degree 3, denominator, degree 4. Okay, so there's nothing, no long division or anything needed here, as we'll get to shortly. And I again count 1, 2, 3, 4 parameters, which makes sense because I've got a fourth order denominator. And generically speaking, this will always be the case. The degree of the denominator tells me how many parameters I should see in the partial fractions decomposition. It's just a pattern to observe, okay, guys? Number 9. Here we have, yowzers, x to the fourth plus 2x squared plus 1. And this is the kind of quartic that you can factor because you just look at it and go, aha, that's x squared plus 1 squared. And so, just like, let me put the previous one up actually at the same time so we can contrast. Just like having x plus 1 squared, or x plus 1 cubed produces this, this, and that, right? This, having that squared, produces the basic thing, which would be a plus bx over x squared plus 1. And then, because it's squared, we do the same thing, but with the denominator squared. And that's actually, this is the partial fractions decomposition for that, like that. Now, you don't see example 9 come up too much, and some textbooks, in fact, deliberately try to hide this, but this is how it works. Now, integrating that is straightforward, but like the dx over x squared plus 1 term, would be like a u substitution, the c over the denominator term for this kind of integration. If it were to integrate this, the c over the denominator we could do by a trig substitution. I forget if I put that in the examples here or not, but don't worry, we'll get back to it on the test. Sorry, little residential calculus humor there for you. All right, let's see here, 3x plus 2 over x minus 3. And so this one, you see degree 1, something has got to give before we do partial fractions. And so much like if you have, 7/5, you can rewrite it as 1 plus 2/5, right? You can write it as a whole number plus a proper fraction. In the same way, we can write a improper rational function as a polynomial plus a proper rational function. The polynomial here is kind of boring, it's 3. Now the way I did that here was sneaky. I just added 0. I said, I will add and subtract 3, because when I do that, I can cancel the x minus 3 from this term, and I can keep the 3 times 3 plus 2, which is 11 over there, and it gives me that. And once I have that, then we can integrate. So this integrates to that, which is that. It's a piece of cake. I say piece of cake, but a lot of people get this problem wrong on tests, because they get so in the mode of the other things we've been talking about, they forget that first order of business is making sure the denominator, the degree of the numerator, is not larger than the degree of the denominator. If it is, long division may be required. For example here, this is third degree, that's second degree. If I'm going to calculate the integral of this using partial fractions, my first order of business is to do the long division. Here it is. So I'll try to go that step by step here. So to divide x squared minus 3x plus 2 into 2x cubed plus 3, I say, okay, so I got to put a 2x up here, because 2x times that gets me the leading term of 2x cubed, right? But then 2x times minus 3x gives me minus 6x squared, gives me 4x. I then subtract that from this. What's it give me? Of course, the leading term cancels by our construction, and this leaves me with 6x squared minus 4x plus 3. Now to get 6x squared from this, I must add 6, right? 6 times that gives me 6x squared. So I get 6x squared, 6 times minus 3 is minus 18, 6 times 2 is 12. I subtract the second one from the first, and that leaves me, these cancel, and then we get minus 4 plus 18, which is, minus 18 is plus an 18. So 14x minus 9. This is the remainder, and the remainder term has degree smaller than the divisor, which in this case is x squared minus 3x plus 2, and so that means we're done. This is the remainder. Thus, this long division shows us that we have 2x cubed plus 3 over x squared minus 3x plus 2 is equal to 2x plus 6 plus the remainder, 14x minus 9 over x squared minus 3x plus 2. And that, we can use partial fractions on this to integrate, right? So I will continue 11 on the next page. Here we go. By the way, remember, the things I'm going through are PDFs which are posted online for your convenience, so you could print these out and follow along if you wanted to. On occasion, we'll have a video where I don't have the thing posted, but for the most part, I'm just looking through the solutions at the moment here. Shut up. So here it is. That's what we found, the piece that, the proper rational function. And then, so this factors into x minus 2 times x plus x minus 1 times x minus 2, which gives me this partial fractions decomposition. All right, cover it up here for a second. And then to get to the next step, I multiply by the denominator. And then what I'm going to do is I'm going to plug in the zeros, plug in 2, plug in 1. Plugging in 2 zeros this out, plugging in 1 zeros that out, which tells me that b is 17 and a is minus 5. To go back up in here, putting it all together, we have figured out that this rational function is equal to that rational function. And so we can integrate this easily with a u equals x minus 2 and a u equals x minus 1 substitution, rather. And there you have it. Integral of 2x is x squared, integral of 6 is 6x, minus 5 log of the absolute value of x minus 1 plus 17 log of the absolute value of x minus 2 plus a constant. May I yet again emphasize that the absolute values are not optional, that they need to be there. All right. Example 12. So here I gave you another example of the denominator being smaller degree than the numerator. Fifth order, second order, we expect there's going to be a third order polynomial that we can peel off using long division. Let's see here. So what I did before I even did long division, though, I just did some algebra. So the numerator I can factor an x squared out. The denominator I can factor out an x. So I might as well just cancel x with one of the x's up here with the x down there, because anyway this expression's not defined for 0, so I'm not losing anything. You know, something that your first semester calculus instructor might not be happy with me about, but I failed to say some things along the line here, which is in every one of these examples, the function's not defined for certain values of x, right? If the denominator is 0, then these are, you know, divergent functions, and so all of these integrals have a certain domain of definition, which I have not emphasized up to this point. All right, anyway, simplifying this with respect to x not equal to 0, of course, we get 3x to the fourth plus x over x plus 1. Now, it's great, but I still need to simplify this, and so then I'll use long division. So there we go. The divisor x plus 1, the numerator there, 3x to the fourth plus x. So, all right, to get that, I've got to put 3x cubed. 3x cubed times x plus 1 gives me 3x to the fourth plus 3x squared. I subtract. That leaves me with minus 3x cubed plus x. Now to get that, I say minus 3x squared times that gives me minus 3x cubed minus 3x squared. Then I subtract again. I get 3x squared plus x. And so I put a 3x here, because 3x times x plus 1 gives me 3x squared plus 3x. I subtract again. I get minus 2x. All right. And then I put a minus 2 here, which gives me minus 2x minus 2. Subtract. I get a 2 at last, the remainder, because this has, you know, 0th degree, that's first degree. And so, poor planning on my part, this is equal to blah, 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 plus 2 over x plus 1. And there you have it. The integral of this is actually equal to the integral of that. This is a polynomial. We love to be asked about integrating polynomials because we just do it. Bop, 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 bop. And this one over here is 2 log of the absolute value of x plus 1, again by that u equals x plus 1 substitution, plus a constant. Did I ever write down the substitution for going from here to here? I did not. Why didn't I do that? Simple, because this is the kind of integration from Calculus 1 that in a Calculus 2 students just expected to do in their head. So if you need to write that down, I wouldn't be bothered. I mean, it wouldn't bother me if you did it. I'm just saying I'm not going to do it, all right? So you should understand what's going on from here to here is a u equals x plus 1 substitution. And goodness gracious, I guess that's the end. So there's a dozen examples of partial fractions. I hope you start to see the bigger picture. If you don't see the bigger picture, you can always ask us questions, okay? Thanks, guys.